All right, let's dive into one of the great unsolved mysteries in all of mathematics. It's a story that's all about chaos and about order and this incredible hunt for a deeper truth that's hiding inside the world of numbers. It all really kicks off with a question that has bugged people for thousands of years. We've got these numbers, right? The prime numbers. They're the basic building blocks for everything in arithmetic. But they seem to pop up with absolutely no rhyme or reason. I mean, just look at them. After 2 and 3, you get a little gap, then they're kind of close together, like 17 and 19, and then suddenly you can have these huge empty spaces between them. This chaotic mess is basically the scene of the crime for our whole investigation.
So, our first stop is right here, digging into this fundamental mystery. For centuries, literally the greatest mathematical minds have been staring at this problem, just trying to find some kind of pattern, any law that could possibly explain all this randomness. And you know what? That search led them to create one of the most powerful tools in all of mathematics. You can think of it like a special kind of map, one that's designed to find order in a place that looks like pure chaos.
Yeah, that's the big question, isn't it? How on earth do you take this infinite, totally unpredictable list of numbers and somehow turn it into something, well, something you can actually navigate and understand? Turns out the answer is a pretty incredible invention.
It's called the Riemann zeta function. Now, don't worry, we're not going to get bogged down in the formulas. They involve some pretty complex stuff. What you need to know is its purpose. It basically acts like a special kind of camera lens. It takes all that messy, chaotic information about every single prime number all at once and focuses it into a brand new picture. The whole process is actually pretty simple to imagine. Okay, so you feed the chaos of the primes into one end of the function. It does its thing, and what comes out the other side is this beautiful, structured mathematical landscape. A world with peaks and valleys that we can explore, especially along this one really important path called the critical line. And that is the real power of this function. All of a sudden, questions about prime numbers can be turned into questions about the geography of this new world. The mystery literally becomes a map.
But, okay, here's the catch. Having a map is one thing. Knowing how accurate that map actually is, well, that's a whole other story. And that leads us to the heart of what we're talking about today, the huge challenge of really understanding and kind of taming the zeta function itself.
This is the absolute crucial question. Just how much can we really trust our map? How precise is our lens? Is it giving us a crystal clear, high-definition picture of the primes, or are there all these blurry spots and weird distortions that we don't even know about? Asking this exact question brings us to our main event. This is the Lindelöf hypothesis. To put it simply, it's a very specific guess about how our zeta function behaves. It suggests there's a strict speed limit on how fast the function can grow, how high its peaks can get along that critical line we mentioned. It's basically a bet that the function is actually pretty well behaved, that it's tame instead of wild. So to really see the difference, check this out. On the left is what we can actually prove today, this wide, fuzzy, blurry boundary. The function could be bouncing all over the place in there. But on the right, that's what the Lindelöf hypothesis predicts, a super tight, narrow, and sharply focused path. It's claiming the function is way more under control than we can currently prove. See, proving the Lindelöf hypothesis would be a game changer. It would mean that our map of the primes is incredibly reliable. It would sharpen the resolution of our best tool and give us a much, much deeper and more confident grasp on that whole prime number mystery. And this is where the stakes get even higher, because proving the Lindelöf hypothesis isn't just about solving some isolated puzzle. It's a huge stepping stone towards cracking the most famous unsolved problem in all of mathematics. Which brings us to the ultimate quest. Now, a lot of you have probably heard of the Riemann hypothesis, right? It's like the final boss of number theory. It even has $1 million prize attached to it. What's so fascinating is that if someone proves the Riemann hypothesis, it automatically proves the Lindelöf hypothesis is true too.
So this makes solving Lindelöf a massive strategic goal. It's considered a bit easier than Riemann, but a proof would be just a monumental achievement. It would give us powerful new tools and insights that could finally light up the path toward that ultimate prize. Which brings us right up to today. The problem has been laid out. The stakes are incredibly high. And right now, mathematicians all over the world are deep in the hunt for a proof. For more than 100 years, this idea has fought off every single attempt at a proof. It just stands there, right on the frontier of our knowledge, a challenge that has forced mathematics to evolve and get more powerful. The answer's still out there, just waiting for someone to find it. And maybe that's the real point, All of this incredible effort and creativity that's being poured into this one problem, it reveals so much more than just a single answer. It uncovers these fundamental connections and structures inside the world of numbers that we never even knew existed. And so we end with this thought. The Lindelöf Hypothesis is this amazing reminder that our universe is just filled with these profound, beautiful patterns, often hiding just under the surface of things that seem totally chaotic. The only question is, where are we going to look next?